Hello students, I hope you all are doing good. So today we are going to discuss magnetism and matter NEET PYQs. So let's begin. This is the disclaimer. Learning objectives. After this lecture you will be able to analyze magnetic field lines, magnetic dipole moment and torque on dipoles in uniform magnetic fields through numerical problems. Calculate magnetic field intensity due to a bar magnet at axial and equatorial positions using given formulas and magnetic moment values. Solve problems related to dia, para, ferromagnetic materials and their behavior in external magnetic fields, including susceptibility. So first question. So consider two idealized systems. First case is a parallel plate capacitor with large plates and small separation. That means area is much greater than the separation between the two plates. Okay, so this is the idealized case when fringing of electric fields at the ends of the plate is neglected, when there is a small separation between the capacitor and large plates are there. Okay, second case is a long solenoid of length L which is much greater than the radius of the solenoid. That means a long solenoid, okay, where length is much greater than the radius of the solenoid, so radius of the cross section. In first case, electric field E is ideally treated as a constant between plates and zero outside. Okay, so in first case, when area of plates is very much greater than the separation between the plates, then electric field is treated as constant between the plates and zero outside. Okay, and magnetic field is, in second case, magnetic field is constant inside the solenoid and zero outside. And in second case, where a long solenoid is there, we assume that the magnetic field is constant inside and constant along the axis of the solenoid, and constant inside and very weak outside means nearly zero outside, or we consider zero outside. So these idealized assumptions, however, contradict fundamental laws as below. So we have assumed these idealized conditions. In actual, magnetic field outside the solenoid is very weak, but it has some value. It is not zero. We assume it. Okay, so however, contradict fundamental laws as below. So options are: case 1 contradicts Gauss law for electrostatic fields, or case 2, that means case 1, that one case is electric field is ideally treated as constant between the plates and zero outside. This case is contradicts the Gauss law for electrostatic fields. Is it correct or not? And B option is case 2. What is case 2? Magnetic field is constant inside the solenoid and zero outside. This case 2 contradicts the Gauss law for magnetic fields. This is second case. Third option is case 1 agrees with E dot dl equal to 0. And D option is case 2 contradicts HDL equal to minus E enclosed. H is magnetic intensity inside the solenoid, okay, which is equal to current enclosed, negative of current enclosed. Okay, so I will give you some time to think about it, that which option is correct. So let's see the solution. So correct option is B. Case 2 contradicts the Gauss law for magnetic fields. How? So using concept 19.12, the electric field lines do not form continuous path, while magnetic field lines form closed loops or closed paths. This is a fundamental reason for this solution. Okay, so electric field lines do not form closed loop. They start from positive charge, end on negative charge. And in case 1, it is written that electric field is ideally treated as a constant between the plates because separation between the plates is very small. So fringing can be neglected, and electric field is constant between the plates of the capacitor. It is known. Okay, it is from positive plate to negative plate and zero outside. We have seen in the capacitor that electric field only exists in between the plates of the capacitor and zero outside. Okay, but magnetic field lines form closed loops. We assume that there is only magnetic field inside the solenoid, but outside there is a zero value. But it is not true, because magnetic field lines form closed loop. Magnetic field is weak outside, but it always form closed loop. If we assume that there is no magnetic field outside the outside the solenoid, then it will contradict the Gauss law. Okay, so let's see. So Gauss law states that this is Gauss law for electric fields. So Gauss law states that over a closed surface, E dot ds is equal to q by epsilon naught. Q enclosed, that Q is the charge enclosed for electrostatic fields. So it does not contradict the electrostatic field, as the electric field lines do not form closed continuous paths. Okay, so if we are assuming a surface that is enclosing any plate of the capacitor, so it will result in Q enclosed by epsilon naught. Okay, so electric field lines are not forming closed loops. So magnetic flux through any surface, closed surface, is not necessary to be zero. And magnetic electric field lines do not exist outside the capacitor plates. Okay, that's why it does not contradict the electrostatic field, as the electric field lines do not form closed continuous paths. Okay, but according to Gauss law in magnetic field, so according to Gauss law in magnetic field, magnetic flux, that is B dot ds over closed surface, is always zero, because inward flux is equal to outward flux. Monopoles do not exist. If we are enclosing any surface around a magnet or any magnetic dipole, so there will be both the poles, north and south. Magnetic flux due to north pole will be outward flux, and magnetic flux due to the south pole will be inward flux, and both this outward and inward flux cancel out, and net flux through the surface will be zero. Okay, it is always zero. So this law states that the net magnetic flux through any closed surface is zero, which is consistent with the magnetic field lines forming closed loops. So magnetic field lines are starting from north pole and ending on south pole. Okay, that means there is inward as well as outward flux, and it is equal, because they are forming closed loop and monopoles do not exist. Even in the solenoid, the magnetic field lines that emerge from one end must return through the other end. But in case 2, we have assumed that there is no magnetic field outside. But if there is a magnetic field along the axis, so after emerging from one end, it must return to the other end to form a closed loop. Okay. So, but in case 2, we have assumed no magnetic field outside the solenoid, due to which closed loop is not forming in case 2. Hence, for this case, B dot ds over closed surface is not equal to 0, which violates the Gauss law for magnetism. Because according to Gauss law for magnetism, B dot ds over a closed surface is always equal to 0. But because in case 2 we have assumed no field outside, therefore integral over closed surface B dot ds is not equal to 0, which violates the Gauss law for magnetism. Okay. Let's see next question. Paramagnetic sample shows a net magnetization of 8 ampere per meter when placed in an external magnetic field of 0.6 Tesla at a temperature of 4 Kelvin. When the same sample is placed in an external field of 0.2 Tesla at a temperature of 16 Kelvin, the magnetization will be. Options are 32 by 3 ampere per meter, option B 2 by 3 ampere per meter, option C 6 ampere per meter, or option D 2.4 ampere per meter. So I will give you some time to think about it. So let's see the solution. So correct option is B, 2 by 3 ampere per meter. So using concept 19.16, what is given? So M1, magnetization. When magnetic field is, when temperature is 4 Kelvin, magnetic field of 0.6 Tesla is there. Then net magnetization M1 was 8 ampere per meter. And B1, magnetic field in first case is 0.6 Tesla and temperature in first case is equal to 4 Kelvin. So what is the net magnetization in second case? B2, magnetic field is equal to 0.2 Tesla and temperature, second temperature is 16 Kelvin. So according to Curie's law, magnetic susceptibility is inversely proportional to absolute temperature, which implies what is magnetic susceptibility? M by H, which is inversely proportional to absolute temperature. Okay, after rearranging, magnetization is proportional to magnetic intensity upon absolute temperature. Okay, since B is equal to mu H, so H is equal to B by mu is constant for a given material. Okay, so material is fixed in this question. Material is not changed. When the same sample is placed, okay, same sample is taken. So mu is constant in both cases. So H will be B by mu. So H is proportional to B. So can we write M proportional to B by T? Here now we are taking small t as a temperature symbol. Okay, capital T is also generalized. In the law it is used capital T, but in this particular question we are using small t. So T, temperature in Kelvin, B is magnetic field induction. So M is proportional to H by T. So H is equal to B by mu. So H is proportional to B. So therefore M is proportional to B by T. Magnetic field induction upon temperature in Kelvin. So by this we can find the ratio M2 by M1 equal to B2 by B1 into T1 by T2, because T is inversely proportional to M. So M2 by M1 is proportional to T1 by T2. Okay, and B is directly proportional, so M2 by M1 is proportional to B2 by B1. Okay, so after putting the values, B2 was 0.2 Tesla, B1 was 0.6 Tesla, T1 was 4 Kelvin and T2 was 16 Kelvin. So after solving this, it will result in 1 by 12. So from this, M2 is equal to M1 into 1 by 12. So what is M1 given? 8 ampere per meter. So 8 by 12, which is equal to 2 by 3 ampere per meter. So M2 by M1 is equal to, so what is the ratio? So M2 is equal to 2 by 3 ampere per meter. Okay. Now next question, the magnetic susceptibility is -4. So magnetic susceptibility chi, which is equal to M by H, magnetization upon magnetic intensity. So it is negative for which type of material? Diamagnetic material only, paramagnetic material only, ferromagnetic material only, or D option, paramagnetic and ferromagnetic materials both. So I will give you some time to think about it. So let's see the solution. So correct option is A, diamagnetic material only. Okay, so using concept 19.13, magnetic susceptibility is given by chi equal to M upon H, NCERT equation 5.13. Okay, So M here is magnetization and H here is magnetic intensity. Okay. For diamagnetic material, we know that diamagnetic materials are magnetized in the opposite direction of magnetic intensity. If magnetic intensity is from left to right, then magnetization will be in from direction right to left. Okay, so what is magnetization? It is a process when all the dipoles will tends to align in the same direction. Okay, so dipoles tends to align in the opposite direction of magnetic intensity in the case of diamagnetic materials. Okay, and we can say this is for this dipole moment theories for paramagnetic material and ferromagnetic material. In diamagnetic material, the theory for dipoles is somewhat different. Okay, it is related with the angular momentum of the revolving electrons. Okay, when we apply the magnetic intensity, then the moment of revolving electron in the opposite direction of if moment of the uh, electron revolving electron, it is creating a current loop, tiny current loop, tiny magnet. Okay, so magnetic moment of this tiny magnetic loop, if it is in the same direction of magnetic intensity, then electron will slow down. If it is in the opposite direction, it will speed up, due to which magnetization in the it is somewhat on the quantum level. We don't discuss it in detail because it is beyond your syllabus. Okay, so magnetization of diamagnetic material is in the opposite direction of the magnetic intensity for diamagnetic materials. So in case of diamagnetic substances, M and H are in opposite direction. Also for diamagnetic substances, amount of magnetization M is very small even if significant amount of magnetic intensity H is there. Okay, so this magnetization value of this magnetization is also very small even if we are applying significant amount of magnetic intensity H. Okay, so therefore magnetic susceptibility chi for diamagnetic material only is negative and low. It is negative because M and H have opposite signs, opposite directions they are, and it is low because magnetization is having very small value as compared to this H. Okay, for paramagnetic materials, this M magnetization is also very small as compared to H, but magnetization in the same direction of H. Therefore, chi is low and positive. And for ferromagnetic substance, this magnetization is high. Okay, that's why this chi value is much greater than 1, means high value of this chi, and also magnetization is in the same direction of magnetic intensity. That's why it is positive also. Okay. So next question. A thin diamagnetic rod is placed vertically between the poles of an electromagnet. When the current in the electromagnet is switched on, then the diamagnetic rod is pushed up out of the horizontal magnetic field. Okay, a solenoid connected to external source behaves like electromagnet. Okay, it has north pole, it has south pole. So it behaves like electromagnet. Okay, you can assume like that. So a thin diamagnetic rod is placed vertically between the poles of the electromagnet, like in the solenoid, in the core of solenoid. Okay, when current is in the electromagnet, means current in the solenoid is switched on, then diamagnetic rod is pushed up out of the horizontal magnetic field. So magnetic field inside the solenoid is horizontal, which is along the axis of the solenoid, and solenoid acts as a electromagnet, a simple electromagnet. Okay, so this rod, when current is switched on, the diamagnetic rod is pushed up out of the horizontal magnetic field. Hence the rod gains gravitational potential energy because it is pushed up against the gravitational pull. Okay, so it gains the gravitational potential energy. The work required to do this comes from, so the work that is being applied on the rod, due to which rod is pushed up, so it comes from options: the current source, the magnetic field produced by electromagnet, the induced electric field due to changing magnetic field, or the lattice structure of the material of the rod. So I will give you some time to think about it. So correct option is A, the current source. So using concept 19.6, as the source of the current is switched on, a magnetic field sets up in between the poles of the electromagnet. Okay, so electric field is being set up due to, as we know that when we switch on the current in the solenoid, electric magnetic field being set up from it, and it is inside the solenoid, it is along the axis, okay, between the poles of the electromagnet. So diamagnetic substance when placed in a magnetic field acquires a feeble means weak, so feeble magnetism opposite to the direction of magnetic field. And we know that diamagnetic substances are magnetized in the opposite direction of the magnetic intensity. So magnetic intensity, or we can say magnetic field, external magnetic field, is along the axis, or from south of the solenoid to the north of the solenoid, inside the solenoid. Then diamagnetic substance will magnetized in the opposite direction, and they will acquire a feeble magnetism opposite to the direction of magnetic field. Also, in the presence of non-uniform field, when there is a non-uniform field, the diamagnetic substances tends to move from strong magnetic field to the weaker magnetic fields. Okay, so they, because the magnetism they have induced is opposite to the direction of magnetic field, so in non-uniform magnetic field they are repelled by the magnetic field. So in the non-uniform magnetic field they tend to move from strong magnetic field region to weaker magnetic field region. So these substances are moved towards the weaker field, so they move from strong to the weaker magnetic fields. Okay, so inside the solenoid there is a weaker there is a stronger magnetic field. Outside the solenoid there is a relatively weaker magnetic field region. Okay, so that's why this rod will pushed up. Due to these reasons, the rod is repelled by the field produced due to the current source. So due to the current source, current flowing through a solenoid or electromagnet, magnetic field is being generated, and due to this magnetic field, this rod is being pushed up. Hence, it is pushed up out of the horizontal field and gains gravitational potential energy. Okay. So due to the current source is a main reason due to which rod is pushed up. So this the work is done by the current source. So next question, an iron rod of susceptibility 599 is subjected to a magnetizing field of 1200 ampere per meter. The permeability of the material of the rod is mu naught equal to 4 pi into 10 to the power minus 7 Tesla meter per ampere. Options are 8 into 10 to the power minus 5 Tesla meter per ampere. B option is 2.4 pi into 10 to the power minus 5 Tesla meter per ampere. C option is 2.4 pi into 10 to the power minus 7 Tesla meter per ampere. And option D is 2.4 pi into 10 to the power minus 4 Tesla meter per ampere. So chi is given, and magnetizing field, that is H, is also given, 1200 ampere per meter. Okay, the permeability you have to find of the material of the rod is mu you have to find. So I will give you some time to solve it. Let's see the solution. So correct option is D, 2.4 pi into 10 to the power minus 4 Tesla meter per ampere. So using concept 19.15, what is given? Magnetic susceptibility of iron is given, chi m is equal to 599. Relative permeability is given by, we know that relative permeability is equal to 1 plus chi m. It is the relation between relative permeability and magnetic susceptibility. So relative permeability will be equal to 599 plus 1, which is equal to 600. So mu is equal to permeability of the material is equal to, we know that permeability is equal to permeability of free space into relative permeability of the material. So that mu is permeability of medium or permeability of the material, which is equal to mu r, that is relative permeability of material into mu naught, relative permeability of free space. So mu naught, we know that value of mu naught is equal to 4 pi into 10 to the power minus 7 Tesla meter per ampere. It is given in the question also. So mu is equal to mu r mu naught, which is equal to 600 into 4 pi into 10 to the power minus 7. So after solving, mu is equal to 2400 pi into 10 to the power minus 7. Hence permeability of the rod is mu is equal to 2.4 pi into 10 to the power minus 4 Tesla meter per ampere. Okay, so next question. Net magnetic flux through any closed surface is, option is 0, positive, infinity or negative. So very easy question. So I will give you some time, think about it. So it is known that net magnetic flux through any closed surface is always 0. So A option is correct. Using concept 19.12, since magnetic field lines form closed loops, magnetic flux through any closed surface is given by closed integral B dot ds is equal to 0. Hence magnetic monopole doesn't exist. Okay. Next question. In a uniform field of 0.049 Tesla, a magnetic needle performs 20 complete oscillations in 5 seconds. So what is given? 20 complete oscillation in 5 seconds. That means frequency is given as shown in the figure. Okay. The moment of inertia of needle is 9.8 into 10 to the power minus 6 kg meter square. If the magnitude of magnetic moment of the needle is, so magnitude of magnetic moment is given, which is equal to x into 10 to the power minus 5 ampere meter square. So this x we have to find. So magnetic moment is given, but only x term is not given, 10 to the power minus 5 ampere meter square. Then the value of x is, options are 5 pi square, 128 pi square, 50 pi square and 1280 pi square. And in the diagram it is given there is a needle having north and south pole and uniform magnetic field is there and it is oscillating in the uniform magnetic field. Okay, so I will give you some time to think about it. So let's see the solution. So correct option is 1280 pi square using concept 19.7. So what is given? Magnetic field B is given, which is equal to 0.049 Tesla. Number of oscillations N is given 20. Time taken T is given 5 seconds. Frequency of the oscillation will be, so frequency will be the number of oscillations per unit time per second. So nu is equal to 20 by 5, which is 4 oscillations per second, 4 per second, that is 4 hertz also we can say. Moment of inertia is given I equal to 9.8 10 to the power minus 6 kg meter square, and magnetic moment M is given, which is equal to x into 10 to the power minus 5 ampere meter square, and this x we have to find. Okay, so the torque on the needle will be tau equal to m cross b, NCERT equation 5.2. So in magnitude, torque is given by mb sin theta. Here tau is the restoring torque and theta is the angle between m and b. Why this needle is oscillating? So needle is the magnetic moment of this needle is along the external magnetic field. We have disturbed the orientation of the needle, due to which it starts oscillating. So we have given the external torque, which is deflecting torque. We have deflected this needle from its equilibrium position, due to which it starts oscillating. Okay, and tau is the restoring torque, which tends to align the magnet or needle again in the direction of magnetic field. So we are deflecting, we are producing deflecting torque, and tau is the restoring torque, and theta is the angle between m and b. M is equal to, m here is magnetic moment, and b here is uniform magnetic field in which needle is oscillating. So in this question, I is equal to magnetic moment of inertia of magnetic needle about any axis passing through its center and perpendicular to its length. M is equal to mass of the needle, and L is equal to length of the magnetic needle. So at equilibrium, deflecting torque is equal to restoring torque. We are deflecting the needle and restoring torque tends to align it in the direction of magnetic field. So what is the deflecting torque? We are deflecting it. So according to, we have seen this formula in the rotational motion chapter. Okay, so tau is equal to I alpha. This is the deflecting torque. We are producing the external torque. We are deflecting this needle from its equilibrium position. So I alpha is equal to, what is the restoring torque? mb sin theta. Why this negative sign is there? So this negative sign is representing something. So this negative sign represents that deflecting torque is in the opposite direction of which torque? This restoring torque. We are deflecting the magnet in the opposite direction to the restoring torque. Okay, so that's why negative sign appears. So I d square theta. So this alpha is angular acceleration. So what is angular acceleration? Like in linear acceleration is equal to dv by dt, and v is dx by dt, due to which after double differentiating, so linear acceleration is equal to d square x by dt square. Similarly for angular acceleration, theta is angular displacement. So alpha, that means angular acceleration is equal to d square theta upon dt square. Okay, which is equal to minus mb sin theta. So negative sign with mb sin theta implies that restoring torque is in opposition to the deflecting torque. For small values of theta, we approximate sin theta equal to theta. Okay, for small values of theta, sin theta is nearly equal to theta, or we can approximate is equal to the theta. So I d square theta upon dt square, which is equal to minus mb sin theta, we can write theta for small angles. So d square theta by dt square, which is equal to minus mb upon I theta. So you don't have to remember this derivation. It is only for your understanding purpose. You only have to remember the final expression of the time period. Okay, which is not given in the NCERT. That's why we are deriving it. So d square theta upon dt square is equal to minus mb upon I theta. This concept is in the NCERT, but direct formula is not given. That's why we are deriving it. So this equation represents a simple harmonic motion. So equation of the simple harmonic motion in the rotational motion is given as d square theta upon dt square, which is equal to minus omega square theta. So this is the equation for simple harmonic motion in the rotational motion case. Okay, so comparing it, we can find out where omega is equal to omega square equal to mb by I and omega is equal to root mb by I. So time period t equal to 2 pi upon omega, which is equal to 2 pi root I upon mb. This is the formula we want to derive. We are going to use. That's why we are doing derivation. So do not have to remember the exact derivation. You only have to remember this formula. That's how this formula is coming. Okay. So time period of oscillation. So t is equal to, which is also we can write 1 by nu. It is reciprocal of frequency, which is equal to 2 pi root I upon mb. Okay. So after substituting all the values, so what is nu? 1 by nu. Nu is 4 per second. So 1 by 4 equal to 2 pi, and in root after substituting I, which is equal to 9.8 into 10 to the minus 6, and m we have to calculate into what is b, it is given 0.049 Tesla. Now squaring both sides, we get 1 by 16 equal to 4 pi square into 9.8 into 10 to the minus 6 upon m into 49 into 10 to the minus 3. So we are writing 0.049 into 49 into 10 to the minus 3. Okay, so after rearranging this equation, m will be equal to 4 pi square into 9.8 into 16 into 10 to the minus 3 upon 49. Okay, so m will be equal to 1280 pi square into 10 to the minus 5 ampere meter square. So after comparing it with the magnetic moment given in the question, which is x into 10 to the minus 5 ampere meter square. So x here is 1280 pi square. Okay, so x here is 1280 pi square. Got it? So let's move to the next question. So match list 1 with list 2. So material is given on the list 2. Susceptibility values is given. Okay, so diamagnetic material, ferromagnetic, paramagnetic, non-magnetic. At susceptibility values, chi equal to 0. Chi is between 0 and minus 1, or it is equal to minus 1. And chi is much greater than 1. And chi is between 0 to epsilon, and epsilon is a very small positive value, means 0 to very small positive value. Choose the correct answer from the options given below. So options are, which matching sequence is correct. So diamagnetic with that A with second, B with third, C with fourth, and D with first. This is matching first list with the second list. Okay, so B option, likewise C option and D option is given. So I will give you some time to think about it and find out the correct option. Let's see the solution. So correct option is A. A with second, B with third, C with fourth, and D with first. Okay. So let's see, using concept 19.1, magnetic susceptibility is given by chi equal to m upon h, NCERT equation 5.13. Okay, so in case of diamagnetic substances, we have discussed in our previous question also that in case of diamagnetic substances, m and h are in opposite directions. Okay, so that's why magnetic susceptibility is having negative and low value. Also, magnetization is very small as compared to the magnetic intensity for both diamagnetic and paramagnetic. But m and h are in opposite direction for diamagnetic only. It is in same direction for paramagnetic as well as ferromagnetic. Okay, so magnetic susceptibility chi for diamagnetic materials only is negative and low. Okay, for paramagnetic substances chi is low but positive, and for ferromagnetic substances chi is positive and high. Okay, for paramagnetic chi is positive but low. For ferromagnetic chi is positive but high value. For non-magnetic substances chi is 0, no magnetic susceptibility. Okay, so this is the susceptibility of different magnetic materials are given below in the table. So this is the correct table which is matching the in front of diamagnetic, it is the correct option. So diamagnetic is equal to the diamagnetic is matched with the second option of the list 2, which is chi is between 0 and -1 and it can be equal to -1. So the case of equal to -1 is for perfect diamagnetism, which is, so the materials, the diamagnetic materials that are showing perfect diamagnetism for which chi is equal to -1 are called superconductors. Okay, so for diamagnetic materials chi is between 0 to -1 or it can be equal to -1. For ferromagnetic materials, value of chi is much greater than 1, high value of chi and positive. For paramagnetic materials, chi is positive but low, between 0 and epsilon. Epsilon is a very small positive value. And for non-magnetic materials, chi is equal to 0. Non-magnetic susceptibility is there. Okay. So thank you. This is all about today's lecture. I hope you understood all the solutions. Thank you.